So we explained the slide before, so we said this will be the TS diagram for Rankine cycle, and then we need to analyze each step. So we have step 1, 2, which is the pump. So we have an equation that we can use. The inlet work to this pump, this is the enthalpy at point number 2, which is pump outlet, minus enthalpy at point 1, which is pump inlet, equal specific volume outlet pressure minus inlet pressure. Step 1, 2 for the boiler, we have an equation to analyze this step. Step 3 for turbine, we have equation to analyze this one. Step 4, 1 in the condenser, we have an equation to analyze this one. We have equation to calculate the thermal efficiency. And we talked about point number 4, which is this point here. How can we find the enthalpy at point number 4? So point number 4, we said it's a mixture of liquid and vapor, so we need to quantify this fraction. So we calculate a parameter called Q, which is the fraction of vapor in a mixture of liquid and vapor. So it relies on the information you have at point 4, the information you have at point 1, and the information you have at point 4 star. And what is 4 star? If like point number 4 is not mixture, if point number 4 is saturated vapor at the same temperature and pressure. So what will be the conditions we have? So these are the whole set of equations that we can use in order to analyze Rankine cycle. So in this example, it says we have a steam power plant. So this one operates on the simple ideal Rankine cycle. So this is the idea of Rankine cycle. This is the TS diagram. Okay. It says we have steam enters the turbine at 3 megapascal, 350 Celsius. So this is the turbine. So the inlet to the turbine, so this is 3. So this is the given pressure, the given temperature. We know that point number 3 is superheated steam. So for superheated steam, we need to know pressure and temperature, which is already given. So you can go to the steam tables, find enthalpy at point number 3, find entropy at point number 3. Then he said here it's condensed in the condenser at pressure 75 kilopascal. So this is the condenser, the inlet to the condenser, the outlet of the condenser 75 kilopascal. So I know the pressure at point 1 and 2. This is very important for point number 1 because point number 1 is saturated liquid. Saturated liquid, saturated vapor, you just need one information to get all the other value for it. So here at point number 1, we have saturated liquid at 75 kilopascal. Then you can find enthalpy, you can find specific volume, you can find any other data at this point. Then we can start use the equations in the that we shown before. So let's see what we have here. So again, we have, so based on given information, so we have point number 3. This one is superheated. Steam at 3 megapascal and 350 Celsius. So this one we can go to the steam tables and then we can find the specific enthalpy at point number 3. This one will be 3116.1 kilojoule per kilogram. Entropy at point number 3, this one is 6.745 kilojoule per kilogram Kelvin. And again, based on the given, again, point number 1 is saturated liquid at 75 kilopascal, which is 0.075 megapascal. So based on this information, then the enthalpy at point number 1, this will be 384.44 kilojoule per kilogram. Also the specific volume at point number 1, which is specific volume at point number 2, which is a specific volume, this one will be 0.001337 meter cube per kilogram. So we have H1, we have H3, we need to find other enthalpies. So we start by analyzing the pump. So start with analyze the pump. So what we have for the pump, if you remember, the inlet work, which is H2 minus H1, this is specific volume, P2 minus P1. So what we have here, H2, I have no idea what is H2. But H1, I know this value. So this one here is given 384. Okay. 0.44. We have specific volume. We just found it, which is 0.001037. We have the P2, this is 3 megapascal. 3 megapascal, which will be 3 times 10 to the power 3 kilopascal. P1, this one is 75 kilopascal. This is here meter cube per kilogram. This is here kilojoule per kilogram. So just to note, focus on the units again. So here I left this kilojoule because here I left the pressure kilopascal. I can convert the pressure to Pascal, but then the left side should be in joule, not kilojoule. Okay? So the units will be consistent. So if you substitute in this equation, then we can find H2. And the value of H2 we have here will be 387.47 kilojoule per kilogram. So again, so let's see what we have so far. So far we have H3, we have H1, and now we have H2. So what is missing? Just to find H4. And H4 we have an equation to find it. But this equation based on calculating the quality, Q. So we need to find what is the value of quality. So here we need to find the quality. To calculate H4. And what is the equation we have for quality? So this is the equation we have. Quality, this one will be entropy at point number 4 minus entropy of saturated liquid at the condenser pressure divided by entropy of saturated vapor at the condenser pressure, entropy of saturated liquid at the condenser pressure. So this is the equation for the quality. What we have in this equation, so we have S4. Actually, we don't have S4, but we have S3. And 3, 4, this point and this process in the turbine is isentropic, so have constant entropy. So this one, entropy at point number 3, this is same as entropy at point number 4. So we have this one here. This will be 6.745. Okay. For the S liquid, so the pressure or the entropy of saturated liquid at the condenser pressure, so this is the same as point number 1. We didn't calculate it, but we can return back here. For point number 1, we can find entropy at point number 1, which will be entropy of the liquid we have. And this number, let me get it. and this number we have here will be 1.2132 kilojoule per kilogram Kelvin. So we have this one, we have this one, both of them will be 1.2132. So what is missing is SV. This one will be the entropy of saturated vapor at the condenser pressure. So what you need to have, what is the condenser pressure? The condenser pressure is 75 kilopascal. So you need to go to the appendix and find specific entropy for saturated vapor at this pressure, 75 kilopascal, and this one, if you find it, this will be 7.4556 kilojoule per kilogram Kelvin. So we have this one here now. So now after we substitute in this one, then we can put this one here, then you can find the quality, and the quality we have will be 0.8861. Then we need to use this quality to calculate H4. So now we have H4. This one will be H of liquid plus quality, H of vapor minus H of liquid. So again, luckily we have this one is H1. This one is H1. This one we need to find, similar to this step, at 75 kilopascal, what will be the enthalpy of saturated vapor. So this one from the appendix at 75 kilopascal, then specific enthalpy of saturated vapor at this one, this will be okay, I don't have number, but we can find this number. I don't have it. Then you can substitute in this equation, and then we have H4 at the end. So this one will be 2403 kilojoule per kilogram. And this will be the last value of the enthalpy we need to find. Now we have 4 enthalpies, then we can use all of them to calculate thermal efficiency. So once you have H1, H2, H3, H4, so basically you are done, because now we can find Qin. So Qin, this will be H3 minus H2. This will be 2728.6 kilojoule per kilogram. Then you can find Q out, which is H4 minus H1. So H4 minus H1, this will be 2018.6 kilojoule per kilogram. Even you can find the network, W net. So the network, this is Q in minus Q out. So if this is required, also you can find this one. And this will be 710 kilojoule per kilogram. So you have all these values. Then you can find thermal efficiency. So thermal efficiency, this one is the network divided by Qin, or 1 minus Q out divided by Qin. just any of the numbers that you have. So you will find the thermal efficiency will be 0.26, which is 26%. So this is the thermal efficiency of this Rankine cycle. So this is what we need to find at the end. So if in the same problem I told you, okay, so can you compare this efficiency with what we can have if we have Rankine cycle, Carnot cycle. So here let's assume that we have Carnot cycle. So everything is reversible, everything is isothermal, or the pump and the turbine isothermal instead of isobaric. The boiler and the condenser are, the turbine and the pump are isentropic. The boiler and the condenser are isothermal, not isobaric. So we can find thermal efficiency, and this special equation only for Carnot cycle. So this will be 1 minus the minimum temperature you have in your cycle, or the lower temperature divided by the highest temperature you have in your cycle. Or when we set this equation, we put it this way: 1 over TL divided by TH. So note that TL, this is the minimum temperature that we can have in this cycle. TH, this is the maximum temperature that we can have in this cycle. So according to this example, TL, this one is 91.76 degrees Celsius. So I need to convert it to Kelvin. So 91.76 plus 273 Kelvin. And sorry. This number was not given in the example itself, by the way. So how we find this number? So if you see here, we have this pressure, 75 kilopascal, and I know that point 1 is saturated. So I find this one by knowing by the following. So I know that state 1 is saturated liquid at 75 kilopascal. Then if you use this information, so from appendix, we can find the saturated temperature, which is TL in this example. T high in this example, the maximum temperature we have, which is 350 degrees Celsius. This was given. But again, I will convert it to absolute temperature. So 330 plus 273 Kelvin. So if you substitute, then we can say thermal efficiency of Carnot cycle, this will be 0.415 or 41.5%. So if you can operate this cycle as a Carnot cycle, the maximum efficiency you can have is 41. But again, this is the highest number. You can't achieve this number. So any real cycle will have an efficiency less than this one, even not equal to this one. Okay, so when we calculate or find the efficiency based on Rankine cycle, so what we find is the efficiency we have is 26. So this is the maximum efficiency we can have in this example.